Hi there. Welcome to a Q&A edition of Space Nuts. My name is Andrew Dunkley, your host. Good to have your company again. Questions coming today from Pete. He's looking at the collapse of the universe. Wants to know where he needs to be when it happens so he gets a good view. Actually, I think it's about something else. We've also got a question from Tad, who has brought up a really interesting point about falling into a black hole from an observer's perspective. If we were to watch someone or something do it, it really is a great piece of science to talk about. Mark is bringing up something from an episode 4 years ago, I think, Antimatter stars. And Dave wants to know about the best time and place to aim a camera for low-light astrophotography. That is a great question. I've had so much trouble with that myself. We'll get stuck into it right now on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And here he is again, Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Fancy seeing you here.
Yes. And we're in similar coloured shirts today.
That's right. I think we're very chic.
Green. Judy reckons green's my colour, but I've never really liked green. But anyway, she's more of a fashionista than I am, so I'll take her word for it. How you been?
Very well, thank you. Yes, all seems to be going well so far.
You look and sound as well as the last time I saw you.
Well, that's right. It seems like only a few minutes ago. That
it does, doesn't it?
So yeah.
Funny that. That's because of a black hole.
It could be a black hole phenomenon.
Yeah, time dilation.
Time dilation.
Although we must point out that this will be your last show for a short while. You're taking a bit of a trip, which will take you into time zones that are just not compatible with life on Earth in Australia. So we will be bringing our stand-in Jonty Horner in to look after things while you're away for about 7-ish weeks.
Something like that.
We knew this was going to happen this year with me away for 3 months and you away for a couple of months. So we knew this was going to happen and we planned ahead so that the show could go on. So anyway, we'll look forward to chatting with Jonty and wish you well on your trip. Where are you going?
We've got about 2.5 weeks in Japan. Then we're back in Australia very briefly, and then we're off up to Ireland for a Dark Sky conference and skipping over to the UK to hang out with my family for a little bit in the UK, and that'll take us to the end of November.
Why wouldn't you? It's just a short hop, isn't it? Really?
Yeah, that's right. Yeah, it's stupid going to Ireland, but going to the UK. That's right.
Yeah.
So we'll do a few things. We're going to, Marnie's got a nice itinerary for us. We're going to go to places that I've wanted to go ever since I was a child and never made it in the UK. So that's
fantastic.
We'll tell you about it when we get back.
I'd love to hear about it. We better get into the questions.
Well, I should, yes.
Yeah, I guess so. Yeah. Our first question's an audio question coming from Pete.
Hi, Fred and Andrew. Pete from Long Point. Got a question. I know that there's contested as to what's going to happen in the future with the universe, the kind of Nang, or however it's pronounced, or expansion, or the Big Rip, or whatever. But question, if the universe is going to collapse back in itself, I get the concept of the gravity bringing sort of physical matter back together, and I know that's only, 5% of the universe, but I don't understand how that would work with the basically pulling of light backwards. So you have light is expanding ever increasingly, obviously at the speed of light. Basically, what happens with that in the event there is a collapse back to another singularity? I'm confused. Thanks, guys.
Yeah, I think a lot of people are. He was referring to the Gnab Gib, which is the reverse Big Bang. Yeah. But it's an interesting question because if it does happen rather than a big rip, the universe stops expanding and then starts receding back in on itself, what does happen to the light and the dark matter and all that other stuff that we don't understand?
Thanks very much, Pete. A great question, which has arisen because I think it might be while you were away, Andrew, we covered the new observations that have come from the dark energy instrument, which is on the Mail telescope. It's a telescope very similar to our Anglo-Australian telescope, which has been surveying the universe, as you do with such instruments, getting the redshifts, which means the distances of all the galaxies, and building up a map. And that map has just the first hint that the acceleration of the universe, which we attribute to this dark energy, whatever it is, the acceleration of the universe is actually slowing down. It's still only a hint. It's not confirmed yet. But if the acceleration is slowing down, then it does raise once again the possibility that we talked about a lot in the 1970s and 80s, the idea of an eventual collapse, a reversal of the expansion of the universe to a collapse. And the end product of that is often called the Big Crunch, but we like the Gnab Gib, that was the name that Brian Schmidt gave to it. It's a great name. So what happens in the Gnab Gib? Well, it is interesting. You've got gravity taking over, and it doesn't just sort of bring together the objects in space. It doesn't just collapse all the galaxies towards one place. It actually collapses space-time with it, because the matter bends space, we know, and that bending is effectively what you would call the collapse in the run up to the run down to the Gnab Gib. And so, in a sense, the light. So what I'm saying is that the distances that are crossed, the distances that we measure between galaxies becomes less, but it's because the space-time has shrunk, basically, and so not just that the galaxies have got closer together, and that means that yes, light will still continue to travel through space-time at 300,000 kilometers per second, but that space-time has got less space in it. Yeah. And so the light just shrinks with the universe. It doesn't kind of escape or anything. The many gazillions of photons that are currently traversing the universe, and will continue to do that as long as things are shining and there's energy to provide that, they will have shorter distances to go. And we will find that the universe just gets smaller. As it gets smaller, the light goes with it. And we end up with a bundle of stuff, subatomic particles, including photons, particles of light, a whole lot of stuff that is going to hit an almighty singularity, which we might call the Gnab Gib.
Yeah, wow. Correct me if I'm wrong, but didn't we talk in the past about a time where the universe will become dark and cold and there won't be any light?
Yeah, that's right. If the universe continues expanding, then eventually there will be light there, but it won't be able to reach you because it'll be beyond your horizon. So the light will still be going through the universe, but that light source will be receding from us. Too fast for the light ever to get to us. So okay. Yes, it becomes dark and dreary, but yeah, light is still there.
All right, there you go, Pete. It will all be cataclysmic and horrible, and we'll all be a lot shorter by the end of that. So.
Every dimension.
Indeed, yes. Although I'm starting to like the idea of a big rip, because a big rip might open us to another universe and we could all escape.
Well, yeah, maybe. Well, of course, you with the Gnab Gib, you could get the big bounce. It could just bounce back, so you've suddenly got an expanding universe immediately afterwards.
It's hard. Yeah, it's hard to get your head around, and I understand why Pete feels confused, because it really is beyond our imagination in many ways, isn't it?
That's right. Indeed it is.
Thanks, Pete. Great question. Hope you're well. Let's go to a question from Tad. This one's really interesting. We understand that due to extreme gravitational time dilation from the perspective of an outside observer, anyone falling into a black hole takes an infinite amount of time to cross the event horizon, even if from that person's perspective they actually do in real time. If this is true, how do black holes and their event horizons even form in the first place from an outsider's perspective? And does this mean that technically nothing has ever fallen into a black hole from our perspective here on Earth? I love this question. Thank you, Tad. He's bringing up the point where if you're watching someone fall into a black hole because of the effect, the gravitational effect on time, space, it never happens. But that person experiences it in real time, until they get spaghettified. So, how come we see black holes when this effect should suggest we should never see it happen? Is that what he's saying?
Yeah. So, how do black holes form in the first place? So in that regard, that time dilation is a kind of optical illusion because the thing has crossed the event horizon, whatever it is, has contributed to the mass of the black hole. So the reality is, yes, if it's you get spaghettified and then you get absorbed by the black hole itself a gazillionth of a second later. It's from the outside perspective. I've always struggled with this, actually, in trying to envisage it because, you imagine some poor person who's fallen into a black hole. It'd be like the, those chalk things on the road where somebody's got hit by a car. There'd be this chalk mark of somebody on the surface of the event horizon. But they'd also, along with that person, there'd be everything else that's gone into it. And black holes are notorious for accreting material. So all the stuff that's spiraling into it, from an outsider's perspective, just ends up looking as though it's stuck on the surface of the event horizon, even though it's actually been absorbed by the black hole. So it is a kind of optical illusion. Yes, it's very weird. It just means that from, what it highlights is it's all about your reference frame. Our reference frame is an observer looking in from the outside. If you've got the reference frame of the person who's falling into the black hole, things are a lot different. We can watch, from the sidelines and cheer people on as they fall through the black hole event horizon. All we see is them frozen on the event horizon, which must be a very messy place with all the stuff that's falling into it.
Yeah.
So, to me, that transforms what the event horizon might look like. It's probably not that nice sphere of darkness that we imagine, but it's got kind of splattered with lots of stuff. And in fact, we know that the magnetism of a black hole actually plays a huge role in directing material so that some of the stuff is actually accelerated perpendicular to the accretion disk, upwards and downwards. And that in itself is a process that it's very hard to get your head around, how stuff that's swirling in towards a black hole suddenly gets dragged up and shot out the poles of the black hole, top and bottom. So a lot of hard work to conjecture. I hope that helps Tad to envisage what's going on. But because it's all about your perspective, basically.
Yeah. So the black hole has happened. My brain had an idea and it just fell into a black hole. And now I can't remember, but we see the black hole because it's already happened. Is that? That's
well, yeah. The black hole's been created typically in the collapse of a star at the end of its life. So that's a straightforward gravitational collapse. The material of the star basically collapses down so that nothing will hold it out, and it becomes this singularity, a point of infinite density, which is how we define it. And it's during that collapse that the event horizon forms, and you've got that. As I said, it's an optical illusion. That's the main point to recognize. It's an optical illusion as seen from the outside. Yeah. That nothing reaches the black hole.
I'm sure we'll get some more questions on this one, but you've probably opened a can of spaghetti there, Tad.
Yeah, which is great because Jonty can deal with all of that.
Yes, he can. Yeah. Yes, that's for sure. All right, Tad, thank you for the question. This is Space Nuts, a Q&A edition with Andrew Dunkley and Professor Fred Watson. Let's take a break from the show so I can tell you about our sponsor, NordVPN. With NordVPN, you can explore the web securely and privately no matter where you are, whether you're streaming space documentaries, downloading data from the International Space Station, legally of course, or just browsing from a coffee shop. NordVPN has your back. Fast connection speeds, no data logs, and protection across all your devices, including your smart TV, plus access to content from around the globe. It's like having a wormhole to the internet. Sorry about that. Without the black holes. Haha. Right now, Space Nuts listeners get an exclusive deal, nordvpn.com/spacenuts. Huge savings, plus an extra 4 months free. That is fabulous. nordvpn.com/spacenuts helps you stay protected online and gives you everyday access without any fear that your private data will be stolen. That's nordvpn.com/spacenuts. And don't forget to use the code word spacenuts at the checkout. nordvpn.com/spacenuts. Now back to the show.
3, 2, 1.
Space Nuts.
Now, our next question's an audio question. It comes from Mark.
Hi, it's Mark in London in Canada. I just listened to an episode from March 2021, and Fred mentioned the possible existence of an antimatter star and how obviously we wouldn't want to get anywhere near it. But I was wondering, is it possible? Do they exist? And how could we tell? If we're looking at a star from Earth, can we tell if it's regular matter or antimatter? Or what if the entire Andromeda galaxy was antimatter? Would we have a way of figuring that out? Thanks. Bye.
Yeah, I would ask my Auntie Shirley, but she wouldn't know either. Thank you, Mark. Antimatter stars, I remember us talking about them. We do know there is antimatter. There's just a hell of a lot less of it than actual matter, if I recall correctly. Yeah, but if you've got a molecule of matter and a molecule of antimatter and they collide, they just cease to exist. Is that how it goes?
Yes, that's right. Yeah, what you get is, so if you, the difference between a normal matter particle, like an electron, and its antimatter equivalent is the electrical charge is the opposite. So the antimatter equivalent of an electron is a positron. It's got a positive electrical charge. And when two particles like that meet, they annihilate, and what you get is a gamma ray. You get a photon of gamma ray energy, which has a characteristic frequency distribution. We actually, in gamma rays, we call it energy. In light, we think of it as wavelength. In radio waves, we think of it as frequency. But it's the same thing, basically, at different levels of energy. So you get these gamma rays, which will be emitted with a specific and characteristic frequency. And that's the way that you might be able to detect an antimatter star. Mm-hmm. I think this story actually goes back, it does go back to 2021. I've just found the article that we referred to, Stars Made of Antimatter Might Be Lurking in the Universe. It's from Scientific American, a very authoritative source. But what they were starting the story with was something that happened in 2018 when one of the experiments on the outside of the International Space Station, which we talked about in the last episode with great warmth and admiration, it's one of those experiments may have detected two basically nuclei of antihelium. These are antihelium particles. And so you mix that with normal helium and you get gamma rays. And so the question is, where does that come from? And that was the outcome of this, the suggestion that the easiest way to produce antihelium is inside antistars, which we still don't know whether they exist or not. But really, the point of Mark's question is a good one. I don't think we know much more about this since that, that speculation. But what they're suggesting, I might actually read from that Scientific American article and acknowledge the source there. It was written by Leto Sapuna, who's the author of that. And I think it sort of puts it a lot better than I can. Antistars would shine much as normal ones do, producing light of the same wavelengths, but they would exist in a matter-dominated universe. And so as particles and gases made of regular matter fell into an antistar's gravitational pull and made contact with its antimatter, the resulting annihilations would produce a flash of high-energy light. That's the gamma rays I mentioned. We can see this light as a there you go. We can see this light as a specific color of gamma rays. And so one of the teams that they're talking about took 10 years of data, which amounted to roughly 6,000 light-emitting objects. They pared the list down to sources that shone with the right gamma ray frequency and that were not ascribed to previously catalogued astronomical objects. So this left us with 14 candidates. This is one of the authors talking, which in my opinion and my co-author's opinion too are not antistars. But they say if all those sources were such stars, that means one antistar would exist for every 400,000 ordinary ones in our stellar neck of the woods. So we're still struggling to get our heads around this. And I'm not sure whether any more of these characteristic gamma ray flashes have been observed or what the latest is on this topic. But it is a very interesting one. I think thank Mark for raising it again, because it's one we should perhaps look at in a bit more detail. I might try and dig out some stories for when I return to Space Nuts on antistars and see what we've got in that.
Yeah. Do you think they could exist, Fred?
I do think they could exist, yeah. I mean, it's one of the big puzzles of the universe as to why there's so much matter and so little antimatter, when our best theories of the origin of the universe suggest that antimatter and matter were created in equal proportions. So it's one of these issues that keeps on bubbling up and challenging our understanding.
Yeah. I'm probably dredging up the same joke I used 4.5 years ago, but there's a lot of doesn't matter in astronomy as well. See, I can hear Geordie.
You got a laugh from Geordie there, yeah.
But yeah, antimatter stars are right up there with white holes. We've never seen one, but there's certain elements of science that think these things exist, but we've just never found the direct evidence or proof, have we?
No, that's correct. Just along those lines, there's something that cropped up about a week ago, 2 weeks ago. It's a gravitational wave event, which I think dates back to 2019. And gravitational waves measured by LIGO and CAGRA and Virgo, the three big gravitational wave detectors in the world, this particular, and most gravitational waves come from either neutron stars colliding or neutron stars colliding with black holes or black holes colliding. And they always have a characteristic signature. They spiral together, and then when they come together at the end, they produce this characteristic chirp, which is when they merge. And that usually lasts a few seconds, that run up to the chirp. But this one in 2019 only lasted, I think it was a tenth of a second. And one interpretation of that is that it was two very massive black holes. I think that's the way around it goes. Could be the other way around. Anyway, a recent paper from China, and I think this was 2 weeks ago, proposed that you could get nearly the same modeling, because they model these gravitational wave phenomena, if it turned out that what you were looking at was not colliding black holes, but a collapsing wormhole. And that's the first evidence that I think anybody has put forward for the existence of wormholes. But it's still very conjectural, because the likelihood, the model of just two black holes colliding actually fits the data slightly better than the model of the collapsing wormhole. But people are still looking at these things, as they are for white holes, and I hope also for antimatter stars.
Yes. Yeah, well, I suppose there's so much to consider in the universe that some things just don't get the amount of time and attention they probably deserve. But the workforce is spread so thin in astronomy and space science, I would imagine. So, it's hard to deal with everything.
With everything, that's right. There's certainly enough questions to keep us busy for a long time in the world of astronomy.
Absolutely, yeah. All right, Mark, thank you. Hope all is well in Canada.
Roger, you're loud and clear here also.
Space Nuts.
Our final question comes from Dave, and Dave is from Inverell in northern New South Wales, Australia. As someone who is lucky enough to enjoy fairly low light pollution where I live, I like to attempt some nighttime photography now and then. Lately, I've been using the Nightcap app on my phone. I've got that one as well, with the Meteor setting, he says, to try and capture some meteor photos. I find the best time to see a great falling star is just as I'm getting the phone set up, ready to start shooting. Just wondering if you have any advice for when to try and capture a meteor on camera, example, time of night, direction, etc., or should I just wait until a good meteor shower turns up? And how many meteors would we expect to see collide with our atmosphere on any given night? Also, great to hear you back, Andrew, and enjoy hearing your travels. When you talk of Iceland, it makes me very keen to return. Can I ask which company you cruised with? Dave from Inverell. Yes, you can. The answer is Princess. It was Princess Cruises. We made the news early in the cruise when we got smashed just southwest corner of Australia by a squall that knocked the ship over, not completely, 7-degree list, which we took 3 hours to straighten up. I had to go up to the bridge and help the captain by, using my weight to stand at the... No, I didn't. But it was, pretty hair-raising for a while there. We made the news all over Australia, apparently. But, it was the Princess Cruise Line. And we've been with them many times on other cruises, and they're... I really enjoy them. They probably, it's debatable, but I think food-wise, they're probably the best. But yes. Now, and you mentioned the... Sorry, go on, Fred.
I was just going to say, if you want to avoid the rigors of sea travel, you could come with Dark Sky Traveller. We go up to Iceland pretty regularly too.
Yes, well, there's a thought. Yeah. The downside of cruising is it's slow.
Yeah.
I mean, it's very relaxing, but if you do want to get somewhere in a hurry, it's probably not the way to do it. And Dave also mentioned the Nightcap app. I do have that one on my phone. I haven't had an opportunity to really use it because there's too much light around here.
What does it do, Andrew? What's the purpose of the Nightcap?
I haven't got my phone with me, but you can preset it to photograph in low light, and you can either put it in manual mode, or you can have this series of presets where you can, if you know what you want to photograph, it will set up the phone to create the exact situation you need to take that particular photograph.
Okay.
Yeah. It's really good software. But I haven't really had a chance to use it properly, but it can do time lapse and all sorts of things. It's really good gear. When and where and how to take low light photographs, Fred?
Of meteors. That was
meteors.
The crucial thing, from Dave's question. And so Dave up in Inverell will have pretty easy access to dark skies.
That's why? Because they're not putting the electricity on up there for another 10 years. Okay, sorry. Everyone asks, in the 30 odd years I've lived here, people have often asked, do you have electricity where you are? So I couldn't help that joke.
No, well, you do. We did in Coonabarabran as well, but we were at the end of the line. And so if ever there was a thunderstorm, we usually lost our electricity.
You were gone. Yeah, we had that problem the first 15 years we lived here.
Oh, right. Yeah.
Same thing.
But they do have electricity in Inverell, and they also have dark skies relatively easily accessible by just driving up a few kilometres further up the highway one way or the other. So meteors, Dave's question, how many meteors are coming in? Quite a large number. We think it's something like 100 tons, 50 to 100 tons a day. Meteoritic material hits the atmosphere. That's worldwide. But that means there are billions of meteors streaking through the atmosphere because most of them are just specks of dust. And they can, sporadic meteors, as they're called, they can whiz through the Earth's atmosphere at any time. There were people talking about them, the stargazing I was doing at Sea Lake in Royal Victoria last week. Quite a few people were spotting meteors as they flashed through the sky. I was looking at screens, so I missed most of them. But probably the time to really concentrate on, if you're serious, and I think you kind of need an all-sky lens effectively for good meteor photography. The new generation of phones do have very wide-angle lenses.
They do,
but they're not fisheye in the sense that you can see the whole sky. But they're wide enough probably to use. The snag with them is that they've got a low aperture, so a high focal ratio. The ratio of the focal length to aperture. And what you need is a low focal ratio to give you fast imaging. It's what we call a fast lens. Whereas these wide angle ones tend not to have that. And so you're tossing up, the relative merits of a very wide angle view or likely to capture more meteors, or a narrow angle of view but greater sensitivity. So you'll see fainter meteors. So, that's, taking all that into consideration. I haven't tried meteor photography with my phone. I've done a lot of Aurora Borealis photography with it, and that works really well because they're sensitive. But it will be an interesting thing to try. It's the fact that you need the shutter open for a long time, but I guess what you can do is just keep on taking short snapshots. The point I was going to get to is when you think about the Earth in its orbit around the Sun, the forward-facing side of the orbit is where you are after midnight. So after midnight means that you're on the leading edge of the Earth, and that's where you're going to get the most meteors, basically. As the Earth plows through the various clouds of dust, you've got meteor showers, which come from big clouds of dust that the Earth goes through. But these things are always best seen in the early morning when you're on the side after midnight. So that's the best advice I can give. I'd be interested to hear how you get on, Dave, and what sort of results you might get.
Yeah. And if you do get a couple of good ones, send them in and we'll post them on our Facebook page, or you can post them yourself on the Facebook group, whatever you like. Love to see what you come up with. We do get some great astrophotography from Space Arts listeners on the Facebook group sometimes. So, more than happy to have you post them on that page, Dave, and hopefully that will help. But the idea of having to get up and do it at the middle of the night, not appealing, but that's life in astronomy, isn't it, Fred?
It is a bit, yeah.
Yeah. Yep. All right, Dave, thanks very much for your question. Don't forget, if you've got a question, send it in to us because we'd love to try and answer it. No guarantees, of course. But you go to our website, spacenutspodcast.com, spacenuts.io, click on the AMA tab and you can send questions there, audio or text. Just remember to tell us who you are and where you're from, and we'll do the rest. Or Hugh in the studio will, if he ever turns up again. He didn't turn up today. I don't know what he was doing, probably trying astrophotography in the middle of the day. Just never listens to us. That's his problem. Fred, thank you as always, and bon voyage. Have a safe journey. Enjoy your time in Japan and Ireland and the UK, and look forward to hearing about your travels when you get back. And we will welcome Jonty Horner from the University of Southern Queensland with Space Nuts for the foreseeable future. So take care, Fred, and thank you.
Thank you, Andrew. I'll miss you all, but I'll be glad to come back and talk to you sometime before Christmas.
Okay, catch you then. Professor Fred Watson, astronomer at large, and from me, Andrew Dunkley, thanks again for your company. We'll see you on the very next episode of Space Nuts. Until then, bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.